Hi, my name is Roger Fuller. Thanks for coming to hear my talk. Appreciate it. And I'm with Western Washington University, the Environmental Studies program there. I was recently with the Nature Conservancy, and a lot of the work that I'm going to talk about today was work that I led while I was at the Nature Conservancy, and I'm continuing it now at Western. My co-author on this is Eric Grossman with the U.S. Geological Survey. And as I said, Nature Conservancy was a major partner on this. UW Climate Impacts Group was a major partner on this project, and it was funded by the EPA and the Moore Foundation as the two primary funders of the work. So the project was to look at the resilience of estuaries and coastal communities in the context of climate change, and to explicitly look at them together for a number of reasons. My primary take-home message from this talk is that green infrastructure or habitat really plays a big role in the protection of communities from disaster risk like floods and sea level rise and coastal storms, and that at present the green infrastructure component isn't really included in a lot of the adaptation planning processes that communities go through when they think about disaster risk reduction. There's a heavy emphasis on the gray infrastructure component. So what we were trying to tackle is to explore the green infrastructure piece, put them together with the gray infrastructure, and be able to look at things a little bit more holistically. So December 17 was an interesting day in the Puget Sound region. It was, we had a low pressure anomaly, and we had the highest recorded sea level for the Puget Sound area. And so some coastal communities experienced flooding, houses were flooded. There was, at the Port Susan Bay area, there was a sea dike that was overtopped and actually breached near the town of Stanwood. The town of Stanwood is, without the dikes there, they would be subtidal at high tide. So there are changing risks. There's also changing risk with floods, river flooding, and that really affects coastal communities as well. And the Stillaguamish River is really the poster child in Puget Sound for the changing flood. And so this graph just shows the annual peak flow since the period of record, and the 5 highest flows have all occurred recently within the past 10 or so years. In the context of this changing risk environment, we need to think about the things that protect us as a community from disasters. And so there's two principal ways that protection happens. One is through green infrastructure, and one is through gray infrastructure. And we know a lot about gray infrastructure like dike systems and levee systems. We're really good at designing and building those things. We know how they perform in terms of reducing risks, and we know how much they cost to build and to maintain over time. And so we have that nailed down pretty well. We don't really know that for the green infrastructure. At best, in a lot of places, we sort of know that they help things out, but we don't know how much. We don't know how they perform in terms of risk reduction or what their long-term costs might be in terms that we can compare with the gray infrastructure. And so there's this gap between the two. And as a result of that, it's really easy to invest in the gray infrastructure piece, and it's a lot more challenging to argue for investment in the green infrastructure as a part of the thing. Our project was to try to tackle that information gap, to gather information relevant to the green infrastructure piece in the context of gray infrastructure, and to put together some decision support tools that help an evaluation of those things together. In the context of the tidal marshes here, for example, and this is going to be the main thing that I focus on today, they provide a protective function in terms of reducing the energy and the height of storm waves. When storm waves come in and hit the coastline, that vertical structure, because of the vegetation, creates some drag that reduces the energy and the wave height of storm waves before they hit the coastline or the dike or the town or whatever is in the upland area. And so as a result of that interaction, there's an attenuation of waves before they hit the coastline. So to illustrate that a little bit, these two pictures are from the same dike on the same day in the same wind conditions. They're about a half a kilometer apart. On the left, there's a dike with a marsh in front of it. There's the dike right there. And there's very little, if any, waves at all hitting the dike. a short distance away, there's no marsh in front of the dike, and there's major waves that are hitting that dike, splashing over the dike, and as a result of that, there was actual damage to the dike itself because of the storm. So we've got vegetation here. This dike is green, it's grass, it's not armored. This dike here is very heavily armored with very large rocks that are very expensive to place and maintain over time. And so there's a significant effect because of the tidal wetlands on the cost of building and maintaining dike structures over time. Okay, so the thing with green infrastructure, though, is that if the habitat is not resilient, then it can degrade over time substantially, and that affects the risk profile for the adjacent community. So in this particular area, in the Stillaguamish Delta, the marshes have been receding pretty substantially over time, and there was a storm in 2006, a windstorm, that breached the dike in an area where more than 2/3 of that width of the marsh had disappeared. What we started with then is this concept that both green and gray infrastructure is important to communities. And so if we're going to look at them jointly together, and if we're going to understand their effects on the vulnerability of communities, we need to understand some key things about what's driving habitat resilience or vulnerability, as well as what's driving the vulnerability of adjacent communities as well. And so I'm going to talk a little bit about that, starting here with the habitat component. So to really boil things down and make it very simple, there's really two major drivers that affect habitat resilience and that affect the kinds of vegetation that you have in the estuary, where the different species occur, and how productive they are, how much above ground structure you have, like height and density of shoots and so on. And those things are water level and salinity. So obviously water level or the inundation regime is really important and determines what plants grow where and what areas can support plants or not. And then the salinity in river deltas is really important. That spectrum from fresh to salt is really important. And how that fresh water, when it comes out of the river, spreads out in the estuary or doesn't spread out as a result of levee systems really affects the salinity distribution. And as we'll see later, the salinity can have a big effect on the productivity of the marsh and whether that marsh can actually persist or not. So some things that drive the water level. Obviously, topography and elevation is really important. That's a key driver of how much water inundation you get at a particular site. Sediment's really important. So sediments estuaries is where all of the sediment in the basin, in the watershed, ends up, is dumped when the river hits the ocean. And that process builds up the estuaries, the marshes in the estuary over time. And so they're accreting, they're raising in elevation over time as a result of that process. So understanding the sediment dynamics, how much sediment's coming out, where it's going in the estuary is really important. River flow, obviously how much water is coming out of the river affects the inundation regime in the estuary. Tides, how high the tides are, how low they are, what's the difference between the high and the low tide, and how that changes over time is really key. And then storms. When you get storms, they can really elevate water levels pretty substantially, and that's where you really get the risk in particular to communities. In terms of salinity, obviously river flow and tides are the big drivers, and so how much water you have coming out of the river and how that interacts with the tides. That really determines how the salinity spectrum in the estuary manifests. So climate change is having a direct impact on pretty much all of these drivers, and including something like topography through the action on sediment. So the key thing here is understanding that the drivers of the green infrastructure services and the habitat services that are provided by tidal wetlands, those drivers, those things that control that, are not static. They're all changing and they're all sensitive to climate. Okay, I'm going to shift a little bit to the community end of the spectrum then here in terms of what affects community vulnerability. So obviously things like river flow and floods affect that. Tides and storms affect the vulnerability of communities in terms of water level, and sediment and topography. So this list probably looks a little familiar. And they're changing with climate change, as I said earlier. In terms of protective infrastructure, this is getting back to the green and gray infrastructure idea. There's two ways in which the infrastructure protects communities from the increasing risks. And so understanding the vulnerabilities to those two parts of the infrastructure are really important. So what we did with this project then was to look at those drivers that I just talked about for habitats and communities and really understand what's happening with those drivers and how they affect vulnerability in communities in the estuary. So a big major thing is elevations, and we developed new high-resolution DEMs for all of the deltas. This is showing the Skokomish that combine bathymetry and LIDAR. LIDAR today is a lot better than LIDAR even just 5 years ago or so, and that's really a key thing. So we have much better DEMs than we had even 5 years ago. One thing to think about though is when you're looking specifically at things like dikes, which are the yellow outlined areas showing the LIDAR data, those are long, linear, narrow features, and those have a lot higher error rate with the LIDAR than your overall LIDAR data set will have. So if you're going to look at something like dike systems, don't assume that your 15 centimeter error rate on your LIDAR is the same on the dike. So there's quite a difference there. So looking at vulnerability, these are changes in flood volume over time into the future. And in areas, for instance, like the Skagit, even within the next 10 to 15 years, there's going to be substantial changes in flood risk. Changes in low flows. So low flows affect things like salinity in the estuary. And salinity specifically during the growing summer season, which is when tidal marshes are really vulnerable to salinity penetration into the estuary. And so that affects the ability of tidal marshes to keep up. Looking at historical trends. So here's the Stillaguamish estuary that I showed you an aerial earlier, understanding rates of erosion and habitat loss in the past. So if we just look at past trends, we can start there, and then you start layering on climate change impacts and how that might affect things. And then one thing we did with sediment was to look at the future projections for river flows coming from the Climate Impacts Group, combine that with USGS data on sediment curves, and so that's where they have the amount of sediment load conveyed at different levels of flow. And when we combine those together, we can get projections for sediment in the future based on changes in river flow. And to our surprise, there was a very dramatic shift in sediment load potential as a result just of looking at those hydrology changes. And so if you have a whole bunch more sediment going through the system, that affects all kinds of things like the ability in levee systems to store water and pass water during flood systems. So that's a key thing. We looked at future flood scenarios, so 100-year flood levels now and in the future, adding in sea level rise, comparing the areas that are flooded and at what depths. We looked at sea level rise impacts, and so the flood event on the December 17th happens about on average an hour a year right now, and later it will be up to 29 days a year, and so that's a way of quantifying for local communities the potential effect of sea level rise. So the question comes then, in this estuary, for example, can we improve both green and gray infrastructure together? And we tried to put all of this data together into decision support systems that can help people to make decisions with regards to green infrastructure and gray infrastructure. And one of the things that we developed is a coastal defense model on this website, coastalresilience.org. The coastal defense model lets you model wave attenuation, so you can pick a profile, one of those yellow dots in the map, and click on it, and you get the actual elevation profile shown, and with the actual current distribution of tidal marsh across that profile shown. You can play with the wind conditions and wave heights. You can change water levels to look at different conditions, and you can change the habitat to look at what happens if the habitat goes away. What it does when you run these different scenarios is it returns wave height and wave energy reduction results for you, and so you can look at how the risk profile changes over time. And one thing it does is it looks at levee overtopping, and it looks at your current scenario, your future scenario, and if there was no habitat at all, and gives you a sense of where your levee is. So I was looking at a significant high water storm event, rare event, and it tells me, for instance, in the current scenario, that there's probably going to be some minor overtopping of the dike there. So there's ways of looking at restoration to restore both green infrastructure and gray infrastructure together, and that when you are able to do a restoration project that strategically focuses on restoring key ecological processes like the distribution of fresh water and sediment in the larger estuary, you can end up with a lot more area that's conducive to marsh growth in this case. So my take-home message then is this idea that green infrastructure protects gray infrastructure. If you're going to look at adaptation for coastal communities, you need to include both of them and understand both of them, because they're both very important. And the green infrastructure has a number of features, like being able to self-sustain if it's resilient habitat, which gray infrastructure can't do. Thank you very much.